Hi, everyone, and welcome to SETI Live. I'm your host, Moiya McTier. This is my first time hosting, so hello, everyone. I'm a science communicator and a writer based in New York City. I'd love to know where you are joining us from, so please write it down in the comments. Wherever you are joining us from, I want to say welcome to SETI Live, and thank you for joining us. Also, welcome and thank you to listeners on the podcast version of SETI Live, available on most podcast platforms. Today, we're talking about the atmosphere of TRAPPIST-1e from that exciting system of 7 exoplanets announced back in 2017. I have two guests joining today. The first is Dr. Ana Glidden. She's a postdoctoral researcher at MIT using both observations and theory to study exoplanet atmospheres. And we also have joining us Dr. Néstor Espinoza, an astronomer and mission scientist for exoplanet science at the Space Telescope Science Institute. So lots of JWST work, I imagine.
Oh, yes.
Nice. How are you both doing? How's the atmosphere feeling to you today?
Fantastic. So excited to be here today.
Oh, yeah. Atmosphere is great.
Good, good. I'm curious, what got both of you interested in studying exoplanet atmospheres? It's not like there's a shortage of other things you could have studied in space.
So I got really excited to study exoplanet atmospheres because they allow us to answer a lot of big questions, in particular, like how do planets form and evolve? How common or rare are the solar system planets? Could there be other worlds like Earth? And could there actually be life elsewhere in the universe? And on a more personal level, I actually worked on the NASA TESS mission, which finds exoplanets in between undergrad and grad school. And I got really excited to see how we could learn more about those small planets that TESS was finding. And to date, they've found about 108 small planets.
Ooh. Do you like the small planet atmospheres more than the big planet atmospheres?
I really like both, but the small planets potentially allow us to detect life on other planets, and that's what makes me very excited about them in particular.
Nice. Néstor, what about you?
Yeah, it's a very similar case in my end. I work in a wide range of missions so far, but really, in a personal level, I remember what got me really into exoplanets in general was Star Wars. My mom, I remember, brought me to see the very first movies back when I was like, I don't know, 8 or 9. And since then, I was really excited about the fact that, there's these worlds like Tatooine that has 2 suns right in the sky, and figuring out whether that's real or not. My mom was like, I don't know, maybe you can find out when you grow up. And I grew up, and we're trying to find out if all these kind of weird worlds that are in science fiction make sense. So that's actually what got me into this science fiction from the very beginning, but then physics and astronomy in general. Being able to answer questions like that, like do worlds as weird as those ones in Star Wars exist? And the fact that we can answer to that now, it's pretty exciting. Yeah.
Yeah, I love that trend of science fiction inspiring science and scientists. Have you found any atmospheres that are as weird as some of the worlds you've seen in sci-fi?
Yeah, I think so, and even weirder. I mean, we have seen evidence of atmospheres that are being outgassed as we speak, like caught in the act of atmosphere being removed from their planets, on giant planets. And for the small planet atmospheres, we're actually right now trying to figure out if they are out there around the smallest of stars. So I would say science is kind of beating a little bit our imagination in terms of what science fiction has proposed. Think nature is even weirder than science fiction out there.
Yes, it is. Nature's so weird. Tatooine is maybe as far as our imaginations have taken it so far, but nature has taken it even farther. And it doesn't seem like we have anyone from as far away as Tatooine or other planets here, but we do have Peter from the Netherlands. We have Ken from Finland, and we do have some more local people. We have Alan in New Jersey. So we're coming in from wide and far here. So I saw 2 papers, one by each of you, both about the atmosphere of TRAPPIST-1e with JWST data. This is from a specific program from JWST to study planet atmospheres. Can you tell us more about that program? I think it's called DREAM.
Mm-hmm. Yeah, I mean, Anna, do you want to take a stab at that?
Sure. So the DREAMS team program is all about trying to characterize a terrestrial planet atmosphere, a warm Neptune, and a hot Jupiter. And the idea is that it's really trying to push the limits of what we can actually do with JWST. So we're looking at different types of planets, and we're also looking at some of the larger ones with different observing modes. And we're just trying to see exactly what we can extract from these atmospheres. And we've had some really exciting results so far. For our WST-17b, which is our hot Jupiter, we were able to detect quartz clouds in its atmosphere, which is the first time that's ever happened.
Oh, that's exciting. Néstor, what about you? Are you involved in other parts of this program, or like the same kind of research?
Yeah, no, we're working on these programs together with Anna, in fact. So we dabble in all of the other sides of the house too. In particular, we were leading the papers on the terrestrial side of the house, but we participated quite deeply on the other studies too. So an interesting bit of this program is that it's part of what we call guaranteed time observation. So when people from different instruments, the different instruments that went into James Webb, they had a lot of work behind that, right? To create an instrument and to map it into this beautiful observatory takes a lot of hard work. And in recognition of that hard work, part of the JWST time was given as guaranteed time to these instrument teams. This particular part of the time, which in this project that we're just talking to you about, this was part of the guaranteed time that was awarded to Spectroscopy in particular, which is the institute I'm at here, which we do the science and actual operations of James Webb. So it's really exciting to, you have that kind of like the responsibility of observing something cool. Yeah. And I think we're delivering, right? I think we have this kind of expertise that, Anna is such an expert on the theory side of the house and mapping observations, have people working on the instrument side of the house, and all of us get together and propose and get this and analyze and share with you folks these beautiful observations with this guaranteed time that we were awarded.
Yeah, I'm so glad you did. And I love that you call it a house. Like you're just one big family. You're doing different house chores at the same time. So the data here that you use to study the atmosphere comes from a technique called transmission spectroscopy. What are you actually measuring in that technique?
Yeah, this is a very smart technique actually that Anna's supervisor figured out, Sarah Seeger, back in the early 2000s, right? Maybe it will make a lot of sense actually. Anna, you want to take a stab at explaining it?
Sure. So we don't actually directly observe the planet itself. We're actually just looking at the host star. And the idea is that as the planet passes in front of that star, some of the light is blocked. And that reduces the apparent brightness of the star. And interestingly enough, as that light is filtering through the atmosphere, it's being absorbed at different key wavelengths that correspond to different molecules. And so you can just think about it in the most basic way that at a specific wavelength, the planet might appear a little bit larger if there's a specific gas there. So for instance, CO2 makes the planet appear a little bit bigger at 4.3 microns.
Got it. When I first heard about transmission spectroscopy, I didn't realize that there was that extra step of linking it to the transit because it's changing the apparent area of the planet in front of the star. I thought that you were just analyzing the light as it came through the planet's atmosphere. So that's an important distinction.
Yeah, and some people actually in the literature have figured out that actually the name is a little bit wrong. We call it transmission spectroscopy, but really you're trying to measure that light that the planet blocks, that it's not transmitted because the planet, absorbs it at a particular wavelength. So that might be a little bit of a hint to understanding how this works. We basically play detective work, right? We try to figure out which part of the starlight is being absorbed by the exoplanet atmosphere. And that's how we figured out that there's, methane or water or CO2. And this technique actually, we're explaining this in a textbook form, but these signals are very, 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 very small. And initially, actually, in conversations with Sarah Seeger and a supervisor when she was doing her PhD, initially she was, astounded by the response from the community because everyone said like, there's no way you're going to be detecting that, right? I mean, there's no way an instrument is going to be able to do that. And we are doing just that, you see? So bold ideas, go through if the science is just right.
Yeah, technology is going to continue to advance. And if we can imagine these really cool procedures that technology just isn't ready for yet, time will let us do it.
Absolutely.
Awesome.
Oh, yes.
So you mentioned some methane, ethane. So I feel like now we're kind of getting into details of planetary atmospheres. And I'm so curious, why TRAPPIST-1e? There are 6 other planets in the system. A few of them have been rumored to be kind of habitable. What's special about Planet E?
Yeah, I mean, Planet E, maybe if I can take this stab at that first, and maybe you can add more on this, and I'm sure you have a lot of thoughts on this. TRAPPIST-1e is very special because it's at a distance to the star that is not too close, such that it would be too hot, or not too far away that is too cold for liquid water to be on its surface if it had an atmosphere somewhat like the Earth. Those are big assumptions. Like, we don't actually know if it has an atmosphere. So far, what we really know is the size of the planet, the orbit, how far away from its star is. But what we're trying to figure out is exactly if it has an atmosphere or not, because it's in this very special zone. And if we like map the Earth magically with, like, a flash of our hands, and we mapped ourselves to where TRAPPIST-1e is right now, we will feel maybe a very similar temperature to what we feel right now. So that makes it very special. Now, the other planets are being observed actually by JWST, and they have been followed up by other programs. So all of them are exciting. All of them are very interesting. The TRAPPIST-1 system is just fantastic in many, many ways. But TRAPPIST-1e in particular is special because it's in this very special zone, which we call the habitable zone. I would like to mention that some people love that idea, that concept, other people don't really. Because habitable, when I say the habitable zone, you immediately think like aliens, right? Let's move there. And I will probably ask you not to buy your tickets yet to that planet, because we don't know yet if it has an atmosphere, and if it does, what is it composed of?
Anna, anything to add about what makes TRAPPIST-1e or its atmosphere especially interesting?
I think Néstor really nailed it. It's just kind of optimally situated within that system to be ideally located in that habitable zone, whether we choose to enjoy what the habitable zone implies or not.
Yeah. Well, Ana, you were the lead author on the paper that really tried to constrain what TRAPPIST-1e's atmosphere is. Can you tell us a bit about what the models suggested?
Sure. So I think the biggest takeaway is that it's still equally likely that TRAPPIST-1e has an atmosphere versus doesn't have an atmosphere. We only observed the planet with 4 transits, which was only ever enough to kind of detect potentially a hint of an atmosphere. So the question with our data was, if we assume there is an atmosphere, what kind of constraints can we place on it? And so we came up with this scenario where it's really well fit by a neutral background gas like nitrogen, which makes up a lot of Earth's atmosphere, with another absorber that could be something like methane, which is common in Titan's atmosphere.
Oh, okay. And I remember seeing in the paper that it's probably not Mars-like in atmosphere or Venus-like.
That's absolutely correct. So the molecule that's probably the most detectable in this type of planet over the range of wavelengths that we looked at is carbon dioxide, which is highly abundant in Mars and Venus's atmosphere. And we didn't see any evidence for it. That doesn't mean it's not there, but just with a 4 transit observation, we don't yet see it. So that kind of starts to rule out different regions of parameter space.
Very interesting. I'm seeing an exciting question here from SETI, who asks, are there lessons from TRAPPIST-1e's atmosphere's data that could inform climate modeling and sustainability efforts here on Earth? What do you think?
Yeah, that's a cool take. Yeah. Maybe I can take a little stab at that. That's a cool take because I was really excited to see just a fefew weeks ago, there's been some papers on trying to do kind of 3-dimensional modeling of what TRAPPIST-1e could look like. And from a physics laboratory, the TRAPPIST-1 system is very special. So the star is very small. The star is very red. And so the kind of colors of light that if aliens live there, that they will see on the sky will be very different to the ones that we see here. Now, we see this beautiful yellow/orange star coming out every day in our planet Earth. TRAPPIST-1e, if it had an atmosphere and if it had living beings in it, they would see this really red star coming up, right? And not only that, but the most likely scenario is that TRAPPIST-1e is tidally locked, which means that there's a particular portion of the planet that is always looking at the star in the same spot. So if you really wanted to look at like a sunrise or a sunset, that's not your place, because it will be stuck in one place in the sky, right? So from a physics standpoint, like a mapping of that radiation to one part of the planet always, it's a very different system to what we see in the Earth. It's a pretty good test to all of these models and how they extrapolate out there. So in that sense, it's pretty awesome, and maybe it could inform eventually some climate modeling over here, because it tests this model on limiting regimes, right? Whenever we test models of limiting regimes in any physics system, that we always learn something new. So from that perspective, I think Finicode could. I don't know, Anna, what are your thoughts on that? This is all speculation, of course.
Yeah, it's of course very speculative. So I think, at least from what we could tell with our data, was, again, if we assume that TRAPPIST-1e is tidally locked, it's possible, if there's an atmosphere, that there could be some sort of ocean at that substellar point that's closest to the star. And even though we didn't detect carbon dioxide, there's still enough wiggle room within our data that there's enough that could act as a blanket to even allow for like a global surface ocean.
Okay. And I love speculating about different types of planets, and maybe if you find that there actually is not much carbon dioxide there, maybe there could also be a lesson there. Nice. Yeah, that's a fun question.
Yeah, I think when before JWST launched, I got asked many times, like, what would be the thing that you're waiting for the most from the telescope, right? And then we have many like standard answers to give to that. But the one that I really love giving, and I still give it to this day, is exactly something you hinted at, Moiya, which is the fact that we might find that these planets are very, very alien to what we expect from the solar system. And that would make me very, very excited. Like that would be super awesome to see something completely outside of what you were thinking, which I think maybe it's pretty likely that it's something like that. Whenever we have base or inferences or extrapolations on the solar system, we typically fail at doing that. And we see the planets and we think, well, yeah, they're different to the solar system. So this might be the case too. So
yeah, I will always keep my fingers crossed for a fun surprise to a surprise solution to a mystery out there in space.
Oh yeah.
So we don't know exactly what the atmosphere of TRAPPIST-1e is like. It seems like there are many possibilities, but would any of the possibilities returned by the model be more exciting to you than others? I'm especially interested in Anna's answer.
Yeah, I would say anything that allows us to potentially have that surface ocean is, of course, very exciting, because it leads into questions about habitability and the search for life elsewhere. But there's many different types of atmospheres that could potentially have enough greenhouse warming to support that. And, the jury is really still out if there's an atmosphere there at all, and if it's one that's going to support that.
Okay. Do you ever let yourself just really run wild with thinking about what the surface underneath a potential atmosphere on TRAPPIST-1e could be like?
Yeah, I mean, you really don't know if there's going to be oceans or lakes or continents or anything like that. It could be quite different than our own solar system bodies. Or it could be something more close to home.
Yeah, absolutely. Néstor, what about you? Are you hoping for any of these atmosphere models?
Yeah, I mean, I try as hard as I can not to force my priors into it, but I mean, anything that could be, as Anna said, habitable in some way are the ones that sound more exciting to me. But to be very honest, finding that it doesn't have an atmosphere and that it's like a place in which you don't want to go in your next vacation destination, it's also an exciting answer as well. It could teach us that we're special here at Earth, or to love even more our planet, take care a little bit even more of our planet, and love our star too. The sun is pretty awesome. It's pretty far away. We don't have to handle its activity so often. So yeah, we might be, that answer might be also pretty cool on its own.
Absolutely. A null result or a kind of disappointing result always teaches us something. So they're still worth it. We have, go ahead, Anna.
Yeah, and if we don't detect an atmosphere, it leads way to kind of characterize the surface, which is a whole nother field of study that's quite intriguing.
Yes, my first paper in grad school was developing a method to find mountains and other topographical features on the surfaces of exoplanets. So I would also love that, because atmosphere has actually just got in the way of studying exotopography. Truly, in astronomy, one researcher's trash is another researcher's treasure. I feel like we can't have a conversation about planets around a red dwarf star without addressing this question. Joe Brooks on X asked, "Aren't red dwarfs like TRAPPIST-1 poor targets when searching for life-bearing planets?" I have heard that a lot. What's your stance?
So, of course, these stars, they're small, they're cool. Some people have described them as angry because they have so many flares, are potentially stripping these planets of their atmospheres. But at the same time, with our current telescope technology, we're kind of forced to go to these smaller stars. TRAPPIST-1 is about the size of Jupiter. And in order to get that contrast ratio between the radius, if you want to look at a terrestrial planet, you've got to go to these small stars for now. And it's possible that as they've evolved and time has progressed, they still could have secondary atmospheres that haven't been entirely stripped from the planets themselves. So I don't think it's a false hope to look around these red dwarf stars, but they definitely do lead to some additional complications that we don't have to deal with here on Earth with, as Néstor said, our nice, quiet sun.
Yeah, go ahead.
Oh, sorry, go ahead, Moiya.
I was just going to say, I like to describe where we are as the suburbs of the galaxy. We're in, just like a nice Victorian house with the sun as our central solar system thing. Go ahead, Néstor.
Absolutely, but there might be other mansions out there that might be even better than here. And that's something I would like to address with this question too, that to kickstart life, one of the key hypotheses has to do with having enough energy incoming into your planet to kickstart that life. And there's some researchers out there, Supit Ranjan being one of them at the University of Arizona. So Professor Ranjan, which works with us too, he has actually proposed that maybe some of these M-stars might be even better in terms of energy, because they emit a lot of this energy, and maybe these planets can thrive with that energy and kickstart life even easier in some of them. So we're still on the lookout. Where all of this is a lot of theory trying to map what we know right now or what we expect right now out there, but now we're observing. So I think I wouldn't classify them as poor targets for searching for life-bearing planets. I think we don't know, and there's arguments for them and against them, but the only way of answering and settling the debate is looking, figuring it out with data.
Yes. Always more data. And there are more ways to be habitable. There are way more factors that go into that equation. We have a question here that I think addresses another one of those factors, magnetic fields. Is there a way to see if a planet the size of TRAPPIST-1e has a magnetic field?
That's very tough observationally. However, there has been papers out there. I remember one like a couple years ago that just because of the radius and the mass that these planets have, then you can kind of figure out what kind of internal composition they might have. And with that and the orbits that they have, the possibility of them having magnetic fields that are actually locked with the magnetic field of the star is not out of the question. So while we cannot observe this right now with our current technology, we can figure out via theoretical model if this is a plausible thing given the system, right? And there's people thinking deeply about this.
Ana, you do theory work and some modeling. What would that look like if you wanted to model these magnetic fields, or is that not something you do?
I don't actually model magnetic fields, but I did look into them a little bit when we were trying to decide, just based on theory alone, if TRAPPIST-1e is likely to have an atmosphere or not. And so you might think, based on our own planet, that a magnetic field might help another planet to hold on to its atmosphere, but it actually can be the opposite case when you have a situation like Néstor described, where that can actually lead to a lot of atmospheric escape out the poles.
Because the particles are following the magnetic field out of the planet and into the star's influence. Potentially. Sounds like potentially another extreme environment that we could study to learn about our more moderate one.
Exactly.
Okay, cool. There are some more great questions in the comments. This one from Thomas asks, are CMEs, or coronal mass ejections, always directed at one of the planets? Meaning, do they always operate in the kind of midplane of a stellar system?
Oh, that's a good question. I don't think we have a clear answer to that. In particular for small stars like TRAPPIST-1. So how we understand how activity and magnetic fields happen on the sun is pretty different to these smallest stars. What you're seeing in the layers of the sun is like radiative transfer. It's just radiation coming out of that, and that's kind of dominating the energy transport in the top of the atmosphere of the sun. Stars like TRAPPIST-1, though, they're what we call fully convective. There is like bubbles of energy going around. And that kind of clashes on how we understand how magnetic fields work on the sun. There's a lot of people trying to figure out exactly what mechanisms will trigger this activity that we see in TRAPPIST-1, for instance. So mapping to that, to where these activity signals like spots or flares or this ejection of material from a star like TRAPPIST-1 happen, it's beyond what current models can say, I think, today. But there's people really, really looking deep into this. I don't know if you have more thoughts on that, Anna.
Yeah, I would just echo exactly what you were saying, that it's still a very active area of research to figure out exactly what magnetic activity looks like for a star like TRAPPIST-1 and how that plays out on its surface.
Yeah, there's so many things to study in this system. I think TRAPPIST-1 is appropriate. It's like the premier system out there I'd like to study. And we have, I think, a very fun question. This is going to be the last one before I kind of wrap it up and ask more about you and the project's next steps. But do you know why it's called TRAPPIST, why the system is called TRAPPIST-1?
Yes. So the reason for this is that this is a survey program. It's a program that it's a small telescope in Chile, back where I was born and raised, in La Silla Observatory. They have the TRAPPIST telescope, and TRAPPIST stands for an acronym that I can't quite remember right now. Maybe Anna or you, Moiya, know. But it's an acronym that is basically a search for planets around small stars. And that's the survey that is looking for this. And this was one of the first strong candidates of that survey. And then it was confirmed, right? But there's many other candidates that have been looking. This is a program led by Michel Guillon from the University of Liège. And they really set out to do something that it was actually pretty tough job. So they were only looking at these very small stars, not like, for example, the mission that Anna was talking about before, TESS. TESS is an all-sky star. You're looking at all the stars, right? But these folks were only focusing on these very small, cool stars and trying to see if they found transits, right? And they did, which is pretty exciting. It's pretty amazing how like a scientific question like that is very focused, turns out to bring these very important systems like this. So we're all very indebted to Michel Guillon and his team for making this project and this program happen.
Yeah. And thank you to SETI in the chat for typing out the acronym for us. It's the Transiting Planets and Planetesimals Small Telescope. But this is a backronym because they wanted it to be named TRAPPIST after the Trappist monks in Belgium, because Belgium was one of the major collaborators in the TRAPPIST mission. And I just love that. So, they also were beer brewing monks. So that's one of my favorite trivia questions. Something like, which planet system was named after beer brewing monks from Belgium? And it gets people every time. Awesome. Thank you for that question. And finally, because we're near the middle of the hour, I'd love to know what is next for this project. What else can we learn about TRAPPIST-1E's atmosphere?
So as I said before, we've only observed it 4 times for this program, and we actually already started our follow-up program, which is looking at it 15 more times. And instead of just looking at TRAPPIST-1E, we're also observing the innermost planet, TRAPPIST-1b. And the idea is that since this small, cool star is very active, it's very difficult to disentangle what we're observing that's coming directly from the star versus what we're observing that can be attributed to the planet's atmosphere. So if you observe the inner planet, which is believed to be potentially more of a bare rock scenario, versus TRAPPIST-1E, which could still potentially have an atmosphere at approximately the same time, so back to back. And then you divide their spectrum together, you can actually potentially remove out the star's light without any need for a very accurate model and without accounting for all the different ways in which we don't necessarily understand M-dwarfs.
Okay, that's exciting. I'm looking forward to that. Nestor, anything to add about next steps?
I would just like to say that that's a very ambitious program, and when we were crafting it, I remember one of the questions was like, "Are you sure this is going to be ever accepted?" Because it's like 130 hours just focused on one star, one system, right? But because we have such like a strong team, because the science case was so exciting, it got approved, and now we're almost at the end of taking all the observations. We have 4 more observations to go from now to the end of the year. Fingers crossed they all go well, and it's going pretty nicely. So you'll be hearing about that program probably very soon on the first results, and throughout hopefully the next few years about the final answers to that program's observations. Yeah.
Pretty soon in the next few years. It's basically a blink away.
Oh, yes.
Awesome. Well, I really look forward to that. And I look forward to reading your next papers whenever they come out. Real quick, do you want to say where people can find you online before we end the program?
Anna?
Sure. You can find me on my website, and also I think I'm on Blue Sky, though I just made that account and don't look at it that much.
Okay, great. That's Ana Glidden. And what about you, Nestor?
On my end, I have a webpage, the personal webpage too, nestor-espinoza.com, and you can also find me on LinkedIn, where I'm most active, I think. So yeah.
Great. Yes, I love following scientists because then you get the early scoop on exciting new research coming out. Awesome. Well, thank you very much, Ana and Nestor. Thank all of you for watching. If you enjoyed this conversation, please like it. Please share it with your fellow space nerds. I know we all come in groups. And subscribe for more space science interviews like this one. Next week, one of our hosts, Beth Johnson, is going to be doing another interview about planet atmospheres and characterization, but this time about really hot, steamy planets. So check back in next week for SETI Live. And remember that SETI is a nonprofit organization. So your donations and your engagement, like subscribing to our newsletter, support the Institute's research and, of course, outreach like this. So thanks again for listening. And until next time, keep looking up and stay curious.